Good morning. Hey, we are at the last chapter. We are on chapter 44. This is Astrophysics and Cosmology. And in this chapter, as you might imagine, we're going to be able to look at, we'll take a quick look at the nearby stuff, some planets and such. But largely, we're going to be looking farther out. We're going to be looking at the stars. What are the properties of stars? How have we come to understand what we understand now about the universe? And nothing provides a better perspective, I feel, than, looking at astronomy or astrophysics. Now, you guys at this point have a really solid background. You've got this great background in physics now. And so what's going to happen for us in this chapter, we do teach an astronomy course here, but this is here at Laney College, but we're going to pack that all into one chapter here, sort of, because you guys have such a strong background. We can move through a lot of the topics pretty quickly, and we can go into a little more mathematical detail. So what this chapter provides for us is, I hope, it's a very engaging set of ideas and things to learn about the universe, and it's going to give us a chance to practice a lot of the tools that we've developed really throughout both semesters. So let's go ahead and get started and see what we can do here. This picture, this one here, and this one, this is a picture of the pattern of photons left over from about 13.7, 13.8 billion years ago, when the universe went through a phase as a high temperature, high density plasma of fundamental particles. So this is kind of like chapter 43 coming back, right? Now you guys have probably heard of this. You've heard of the Big Bang. It's not the best title that astronomers or astrophysicists came up with. So what the Big Bang refers to is actually, it's a phase. It's like a thermodynamic phase that the universe went through. The temperatures at that time were so high that protons and electrons did not stick together. There were no atoms or molecules. There were just free electrons zipping around. There were a bunch of protons zipping around. In addition, there were neutrinos and neutrons that would form and zip around. So think of this as just a collection of a lot of high-energy particles. Now, the protons and the neutrons and such have, since that time, they have condensed out. And so what we have, matter that's made up of different elements or different compounds. But the photons that were interacting with everything at that time, the photons we have left from a very, very early stage of that high-energy plasma, the photon patterns are still remaining. Now, in addition to the photons, just to throw this in here, there are also neutrinos left over from that time. As you guys know from our discussions in earlier chapters, neutrinos are really hard to identify. It's very difficult to identify neutrinos and observe them, but the neutrinos are out there too. So that's, future research will certainly be looking to come up with better ways of understanding patterns of neutrinos. Now, the reason that it's shaped like this, you kind of know when you look at a globe. If you look at the surface of the Earth flattened out into a pattern, you could take like an equator region or something, and you could show what's really on a three-dimensional surface. You could flatten it out, and that's what's been done here. So this is looking out into space in all different directions and then putting it onto one diagram here. The slight differences in color indicate slightly different temperatures, so slightly different energies of the photons that are observed coming in from different regions. Some regions, on average, the photon energies are a little higher. In other regions, it's a little lower. And our understanding is that's what's led to formations of galaxies or galaxy clusters, where the densities first became a little higher versus where the densities were a little lower. That's what has determined galaxy formation since that time. All right, this is a picture of what is out there in terms of the visible part of the spectrum. The leftover photons from the very early Big Bang phase, or the high energy, high temperature plasma stage, those photons are now in the microwave part of the spectrum. This is in the visible part of the spectrum. And you can see these galaxies. Now, this was taken with the Hubble telescope. This is what's referred to as the Hubble Deep Field set of a collection of photos that have been taken. This is just amazing to look through these. They've taken the Hubble telescope, the space telescope, pointed it in different directions. They've taken these very, very long exposures over weeks or months to get views of the deepest objects they can see. And it's just more and more galaxies, right? Every direction you look, space has this pattern of galaxies scattered throughout it. All right, let's get some distance measurements in place. So to measure these really long distances that we're going to need, what we do is we introduce something called the light year. The light year is a measure of distance. It's the distance that light travels in a year. We can take the speed of light, multiply it by the number of seconds in a year, and that gives us the number of meters or number of kilometers in a light year. So it says that a light year is about 10 trillion kilometers. Now, Pluto, the dwarf planet Pluto in our solar system, is about 10 to the minus 4 light years away from us, but the nearest star is at 4.3 light years. So these are just incredible distances. I want to add to that. There's another unit that we use for distance, for nearby observations. The distance from the Earth to the Sun is 1 astronomical unit. Now, I'm not crazy about the name they came up with, but this is a distance measurement, and an astronomical unit is 150 million kilometers. That's the average distance between the center of the Sun, the center of the Earth. It's the radius of Earth's orbit, or the average radius. Now, a light year, which we just defined, is about 63,000 astronomical units. So it says that during the course of 1 year, light would be able to make 63,000 trips between the Sun to the Earth, and then the Earth back to the Sun, and the Sun to the Earth. 63,000 trips back and forth would take light an entire year to be able to do that. Now, 1 light year is 63,000 AU, so that would say that the nearest star, which is a little over 4 light years away, is 271,000 AU. So the distance from the Sun to the Earth, 1 AU. Distance to the nearest star, 270,000 AU. Jupiter's at a distance from the Sun of about 5 AU. Pluto's at about 40. The nearest galaxy, the nearest large galaxy, the Andromeda galaxy, we're part of the same galaxy cluster, the Milky Way and Andromeda are the big guys in the collection of galaxies nearby, 2 million light years away. So you may have noticed too that I'm using for light year, I literally write in a factor of c times year. This works kind of the same way that EV works for energy units. If I'm doing calculations, the c in light years can be canceled out with other factors of c that show up. Now, this is a picture of what we expect our galaxy looks like. This is not our galaxy, it's some other galaxy which appears to share common features. So if this is the Milky Way galaxy, we've got kind of a bulge, we've got kind of a flattened disk. Our solar system is a little tiny, tiny speck out here, not in the central bulge, but out away in one of these spiral arms. So this is showing the size of the galaxy, very roughly, the stars of the Milky Way galaxy in the disk spread out by about 100,000 light years. And because of gravitational effects, you have the formation of these spiral arms. Okay, so nearest large galaxy nearby, Andromeda, 2 million light years away. Light from that galaxy has taken 2 million years to get here. It's estimated that if we take our telescopes like we saw in that earlier photo, if we were to take the telescopes and just point them in every direction, how many galaxies would we end up observing if we had time to look in every last direction and write down every galaxy we see? We're guessing that there could be 100 billion galaxies that could be cataloged, and those galaxies individually have 100 billion stars. So 100 billion stars per galaxy, and again, if we get the funding to do this, we could point our telescopes all over, if we have enough time, to catalog all the galaxies. There could be 100 billion galaxies within our view. So just an amazing set of numbers. Of course, we can't see our own galaxy, the Milky Way galaxy, but what we can see is we can see other spiral galaxies like this. We're guessing that's probably a pretty good representation, the one in the middle, as to what the Milky Way galaxy looks like. Okay, so here's a question or a comment. Astronomers often think of their telescopes as time machines because you're looking back to earlier times. How far back can we look? Let's see. Light takes about a nanosecond to travel 30 centimeters. So if I'm looking at an object 30 centimeters away from me, I'm actually looking at something a nanosecond into the past. Now I know there's processing, there's neural processing that's going on. So I don't experience that vision right away, but just the time delay of the light itself, we would be looking, a nanosecond into the past. Looking at the moon, light from the moon has taken a little over a second to get here. From the sun, it's about 8 minutes. From the nearest stars, it's been 4 years. From the Andromeda galaxy, it's 2 million years. So as we look at objects that are farther and farther from us, we're also looking back in time. So not only do we learn about what the distribution of galaxies and stars are throughout the universe, but we get to see, was the universe different in the past? If we're able to look way, way, way back, can we see objects that maybe we don't continue to observe today? So that answers some of those questions. So you can see how important these distance measurements are. How do we actually go about measuring distances? Well, it turns out that there's there's kind of a list of different ways that we can measure distance. For relatively nearby stars, what we start with is an effect called parallax. So what parallax says is this: look, since Earth is orbiting the sun, we actually get different views of the star field. So if I'm looking at a pattern of stars, some of those stars are going to be closer to me, some of those stars are farther away. If I now walk back and forth or orbit, if the Earth is orbiting the sun, it's kind of like walking back and forth and getting different views of the star field. The ones that are close by are going to appear to shift back and forth as Earth orbits. And that effect is called parallax. And this is just an example. If I have a star that's particularly close compared with those background stars, then during the time that the Earth is orbiting, that star is going to shift back and forth. Now, the more shift that we get, the closer the star is. So we can work through, let's see if I'm using the same notation they're using. I don't think I am. So here is Earth's orbit. Let's say that that's big R. Really? I used big, so I did. I used big R for this. Although I don't see it in any of the formulas here. The distance, this is the one we're really interested in, is how far is that star from our solar system? So I'm thinking of that as some distance, and this is the angle phi. And so R, this distance here, Earth's orbital distance, which is 1 AU, there we go, there is R right there. 1 AU is going to be given by this distance times that angle. And so if we define a parallax angle, half the amount that the star shifts back and forth in angular terms, that degree can be divided up into what are called 60 minutes. Each of those minutes is divided up into what are called seconds. Not crazy about the 60-60, but that's what we have. Let's say that we have that really close star, 4.3 light years away. That's 271,000 AU. That star's name is Proxima Centauri. The angle, the parallax angle that we expect for something 4.3 light years away would be taking the baseline, which is determined by the radius of Earth's orbit, 1 AU, dividing through by the 271,000. It says that a star at that distance, a distance of 271,000 AU, would shift back and forth 3.69 10 to the minus 6 radians. So the way this formula is set up, initially we want to be working, the angles in this formula are going to come out in radians, and then those can be converted into degrees. And so I've switched from radians into degrees. This is working out to be 2 times 10 to the minus 4th degree, or what's using the minutes and the seconds conversions, 0.761 seconds of arc. That is really, really tiny. So, walking back and forth here, trying to figure out how much that star shifts back and forth, that's why parallax was such a difficult measurement to make. So anyway, the parallax angles that we end up with are pretty tiny. So just as a comparison, we could do this. Let's see, here is the sun, here is the Earth, there is that nearest star. If we were to take a tennis ball and let the tennis ball represent the size of the sun, so maybe we have a tennis ball that represents the size of the sun, we have other tennis balls that are these other stars that are way out there. On that scale, the Earth would be a little tiny speck. So, usually, if I'm in a classroom, there's some chalk dust or there's something around that we can use to represent the Earth. So in terms of diameter, the sun's diameter is over 100 times larger than the Earth's diameter. So sometimes it's said that the sun is 100 times bigger than the Earth, but that's just diameters. If we think in terms of volumes are three-dimensional. So the sun is 100 times bigger this way, and it's 100 times bigger this way, and it's 100 times bigger this way. So in terms of volume, that would be 100 times 100 times 100. That would be over 1,000,000. So it turns out that the sun's volume is well over 1,000,000 times larger than the volume of Earth. Now you guys know that Earth is a pretty big place, right? It's a planet, it's good sized, but the sun's got 1,000,000 times that volume. All right, so if we were to get a scale of the solar system where the sun is a tennis ball, and we set it over on that side of the room, And the Earth is a little tiny speck, and we're holding it over here. How far would we need to move the Earth from the tennis ball, from the sun, in order to represent the distance away from the sun? And you go, well, when I look at the sun in the sky, it's kind of this big. We must be a certain distance away. And that distance would be pretty much all the way across the room. So if I put a tennis ball here, I have to walk many, many meters to the other side of the room, 8 or 10 meters or so. That's kind of the scale. So if the sun is the size of a tennis ball and the Earth is the size of a little tiny speck, and they're separated by, 8 or 10 meters. Now, as you orbit the sun, we orbit the sun every year, that's an enormous distance that we have to travel. So how far have astronauts traveled from the Earth? And the astronauts in the International Space Station are only a couple hundred miles away. Their orbit is only a couple hundred miles above the surface of the Earth, 300 or 400 miles, something like that. They're closer than Portland to where we're located. They're not that far away. Now, astronauts have traveled to the moon. How large is the moon on this scale? And moon's orbit is about this big. So on this scale, the moon's orbit actually entirely fits inside the volume of the sun. The distance out to the moon, and including that entire circle or ellipse of moon's orbit, easily fits inside the volume of the sun. So that's as far as astronauts have traveled. We travel much, 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 much farther every year because Earth is orbiting the sun than astronauts traveled when they went to the moon. Much farther. Now, on that very same scale, how far away is the nearest star? So if the sun's being represented by a tennis ball, and this nearest star is being represented by a tennis ball, where should I place that other tennis ball? So the sun's a tennis ball in this room, and the Earth's a little tiny speck on the other side of the room. That tennis ball is in Denver. It's well over 1,000 miles away, based on this scale that we have set up. So just to give you guys an idea of how far away the stars are, even the very nearest ones, they are so much farther away than objects within our own solar system. So these distances are just incredible. So we're going to do we'll do a calculation here using that formula. So how far away is the star? This is kind of a funny problem. What it says is that we've got some kind of a setup here where here is the sun, here is the Earth, here is a star. They're using a right triangle approximation, and it's kind of, okay, so if we start out by assuming that the angle being measured here is 89.99994 degrees, then what we're really after is this parallax angle. So let's say the parallax angle is 0.00006 degrees, and we can convert that into radians. So we want, see, it's that viewing angle that they've given us here. So the feature here is to get that parallel axis and parallel angle, and this is given in degrees. We've converted into radians, and then what we're going to do is we're going to take that 1 AU and divide by that number in radians. Now, radians are unitless. The radians units will drop out, and it says that the distance to that star in AU will be 955,000, just about 1,000,000 AU out to that star. Now, once we've got the number in AU, we can use our conversion factor that we've introduced. This is one of the reasons I like working kind of back and forth between AU and light years, especially in these parallax distance calculations. So now we've got this in AU, we can convert it into light years. It's 15.1 light years out to that star. That's the parallax angle we're going to get. All right, how bright are stars? Well, the brightness of a star, now they're calling this the apparent brightness. I'm not sure how I feel about that. What they really mean is they're different brightnesses. There would be a brightness if we stood right next to the star, and then there's a brightness if the observation is being made from Earth. And so what they're calling apparent brightness, and they're using little b, would be taking the power and dividing through by a spherical surface. Well, wait, what they're calling power is L, and in astrophysics that's referred to as the luminosity. So the luminosity of a star is the power, the rate at which energy is being transferred away. Now, there's a luminosity typically designated in terms of light. So stars aren't just radiating photons, they're also radiating neutrinos, and then they're radiating much, much lower levels of other particles, electrons and protons and such. So we're going to stick with the visible, we're going to stick with light, the entire spectrum, not just the visible part, but the entire spectrum of light, and write down some equations in terms of the power. Now the power is going to be written as big L, because it's luminosity. That would mean that brightness is intensity. So we've seen these formulas before. They're in terms of luminosity and intensity. Now, what determines a star's power output? We're going to come back. We're going to come back and use this formula. This formula is saying that as we get farther and farther away from the star, the intensity is going to drop off, and it's going to drop off with distance squared, and it's going to drop off like the surface area of a sphere, because as we get farther and farther away from the star, its intensity, or its brightness, is going to be reduced because of a distance effect. All right, what is it that actually determines the luminosity of a star? Well, stars are shining because of nuclear fusion reactions in their core. Fusion reactions for most stars, for 90–95% of the stars that are out there, fusion is just hydrogen converted to helium, and yeah, it's just the stuff that we outlined in chapter 42. So this is just chapter 42 stuff. Now, stars that are heavier are able to fuse helium into elements like carbon and oxygen, and even heavier stars can fuse elements like into silicon and iron. Now, these are just representative elements. What we're really saying here is that these heavy stars can generate the periodic table. They can generate at least the early parts of the periodic table. They can be creating and forming within their core through nuclear fusion reactions. They can create elements, and for the heaviest stars, that could go all the way to the formation of iron, isotopes of iron. Now, what happens with a star is this. When a star forms, it's kind of randomly from depending on how much material is in that region. So we're going to have a gravitational force, a gravitational collapse of a large spread out region of hydrogen and helium that collapses to form a star. Now, if it happens to form out of a lot of stuff, if it forms from a lot of hydrogen and helium, that means that there's going to be more gravity. That's going to generate higher core temperatures and pressures. So the higher mass stars have more gravity, higher core temperatures, higher fusion rates, and those are higher luminosity. So that's kind of the bottom line, right? If a star forms, what will its properties depend on? How much stuff did it form from? How big is the star? How much mass does it have? Now, just a reminder, brightness from that previous slide, that's intensity. That's going to be in watts per square meter. And that the formula we've used in previous chapters is that the intensity of light depends on the power of the central source divided by 4 pi d squared, where d is the distance from the star out to where we're making the measurements of intensity. The formula in the book and in the slide before is little b is equal to big L over 4 pi d squared. So those, unfortunately, or fortunately, whatever, those variables are going to get swapped back and forth. I'm going to try and be clear each time we use them. So here's a problem. It's saying how bright, what's the apparent brightness of a star? So let's try this. There they are. They're the two formulas. So we can think in terms of the brightness is the intensity, the luminosity of the star is its total power. So what it's saying is that there's a star, we've identified it to be 10 light years away. I can write that down in numbers of meters. It's got a luminosity. Now, this is kind of interesting. This is actually the luminosity of the sun. So the sun's power output is 4 times 10 to the 26 watts. So this star they're talking about is has fusion reactions that are occurring at the same rate as the sun and producing the same amount of energy at the same rate. But this star is 10 light years away. So a star like the sun, placed 10 light years away, how bright would that be? And that would work out to be 3.56, 10 to the minus 9th watts per square meter. And you're thinking, wow, that 10 to the minus 9 is a small number. Well, yeah, it's starlight, right? And it's a really low number because the star is far, far away. So this would be a star like the sun, placed just 10 light years away. That's a relatively nearby star. And then the brightness is in, 3.5, 10 to the minus 9 watts per square meter. Now, what if we take the sun, which has the same power, the same luminosity as this star we're talking about, but this time it's only 150 million kilometers away. Well, the brightness of the sun observed from Earth is 1400 watts. So you can see it's all about distance, right? Here are two identical luminosity stars. The sun, the brightness we observe from the sun at the location of the Earth, the sun's brightness is 1400 watts per square meter, but this star that's 10 light years away is much, much reduced. So it turns out that, it turns out we can do this. It turns out what we can do is we can say the ratio of the brightnesses depends on the ratios of these formulas. And in this case, it's going to depend on the ratio of the luminosities, and it's going to depend on the ratio of the distances squared. In this example, the sun and this star located 10 light years away have the same luminosity. So this ratio cancels to be 1, but the distances are very different, and that's what's creating the difference in brightness. Okay, so they're saying kind of the same thing here. Stars that have more mass are more luminous. The surface temperature is a separate question. When we look at the light from a star, we're really just seeing the light from the outer layers. We're not seeing light coming from deep inside the star. So we're able to come up with a surface temperature, but the surface temperature doesn't really tell us what the core temperature is. The surface temperature is not necessarily going to tell us what the luminosity is. We have to know there's more going on within that star other than just the surface temperature, but the surface temperature is going to be useful. So we find that surface temperatures on stars range from about 3,500 Kelvin all the way up to about 50,000 Kelvin. Now the general trend is that higher surface temperatures do correspond to higher luminosities, but there are exceptions, and so that's what we're going to have to look at. So these are different, what are called spectral types, and what we can say is that these different color stars really have to do with the surface temperature. So these blue stars, these blue giants, something like Rigel in the constellation Orion, versus a red giant, a star like Betelgeuse in the constellation Orion, you're seeing good examples of surface temperatures of 3,000 Kelvin versus something at 30,000 Kelvin. Okay, we're going to make the connection in this example between surface temperatures and star diameters and luminosities. So let's see how this would work. First of all, what we can say, let's take two stars, star A, star B. Star A has a certain surface intensity. So this is the surface intensity. And this takes us back to, well, we saw this in thermodynamics. So I think we saw this formula way back in chapter, I want to say chapter 19, maybe. So this was the rate at which radiation is coming off an object in terms of photons. And then this is the surface area. So if I think of this as a star, this is the, we also saw this in chapter 37. So that's the more recent time that we've looked at that formula. And we spent a fair amount of time on this. So this was the early part of chapter 37. We said this is the surface intensity of light coming off of a star or a planet is given by the Stefan Boltzmann constant times temperature to the fourth power, and then this is the combined surface area. So the total luminosity is related to the surface intensity and the surface area. Now what's causing the luminosity, I always want to make this clear, what's causing the luminosity is the rate of fusion. But by measuring surface temperatures and by measuring diameters of stars, it has to be the case that the diameters of the stars, or the radiuses, and the temperatures are related to luminosity just by the way thermodynamics works. So we can think of it this way. We're able to look at the light coming from a star, look at the pattern, look at the spectrum of light, and determine a surface temperature. By observing a surface temperature, we have information that will allow us to possibly determine the diameters of these stars. So that's usually where these sorts of calculations are headed. So if I start working in terms of ratios, so I'm comparing two different sorts of stars, the Stefan Boltzmann constant cancels out, and I'll have a ratio of surface temperatures to the fourth power. Times, what's also present here is this radius ratio squared. So let's solve this in terms of radiuses. So the ratio of radiuses, which is the ratio of diameters, comes from taking the square of the ratio of surface temperatures times the square root of the luminosities. So if I've got two stars, where one of the star has twice the surface temperature, so if one star has twice the surface temperature, but the luminosities are the same, then it would say that the star with the lower surface temperature needs to have a diameter 4 times as big. Okay, so the luminosities we're going to say are the same of two stars. They have the same fusion rate, but because the star itself, the material that the star is made out of, for whatever reason, is more spread out in this star compared with this one, even though they have the same luminosity, that star is going to have a higher surface temperature and this one will have a lower surface temperature. Okay, so these ratios are pretty handy. Let's look at this a little bit more. So we're going to say here is star A, here is star B. We've observed the peak wavelength in the light that's coming from these stars. For star A, we observed that its spectrum peaks at 700 nanometers. Now that's a red star, right? 700 nanometers peaking. 700 nanometers would be very much in the red part of the visible spectrum. For star B, the spectrum peaks at 350. Now that's actually a little bit into the ultraviolet. That's going to be a very blue star. So we're looking at a red star and a blue star in terms of peak wavelength. And then what we can do is we can bring out, this is again from chapter 37, a relationship between the temperature and the peak wavelength and the constant, 2.90, 10 to the 6 nanometers Kelvin. This was Wien's law from chapter 37. That enables us to identify temperatures, surface temperatures, for these stars. So this star is at 4140 Kelvin, and this star surface is at 8280. So the temperatures differ by a factor of 2. Now the surface intensities, which are given by sigma times t to the 4th, are going to be quite different because this has twice the temperature. This is going to have 16 times the surface intensity. Now, we're going to assume that both stars have 25 times the luminosity of the sun. So this was all given in this example, so I just wanted to come back and refer to this slide. So we've made measurements of these stars, and we've identified that they both have a very similar overall luminosity. And then we've identified peak wavelengths. Use Wien's law and the Stefan-Boltzmann equation to find surface temperatures and the relative size between the stars. So that's what we're in the process of doing. And so we're going to say that the luminosity of each one of these stars individually, 25 times as luminous as the sun, that would put it at 1 times 10 to the 28th watts. And then putting the numbers in, the surface areas then that we would calculate. So coming down to saying the luminosity is the surface intensity times the surface area, and that's equal to, well, this is I surface and I area, and those are the items that we've calculated over there. So we're able to calculate how much surface area these two stars have, and then work back and figure out what their diameters are. So we did everything in terms of ratios here. There was enough information given. We could come back and just fill in all the numbers. So we didn't just have to say one star has 4 times the diameter. We could actually calculate what those diameters are. So that stuff that we learned back in chapter 37 and then earlier in thermodynamics, we can now bring that back and use that to help us understand the properties of these stars. Now, when we look at stars, you could look out and start collecting information about all of their properties. And so distance is kind of the most important thing that we have to start with. We got to be able to measure the distance out to the star, because unless we know the distance, we can't determine the luminosity. I can't look at 2 stars in the sky and go, that one's more luminous than that one. I just don't know, because luminosity refers to their actual energy output, and I don't know how far away these stars are. So it could be that the star that's very dim is actually much more luminous, it just happens to be farther away. Now, once we've got the distance information figured out, and we talked about parallax as an example of how distance could be measured, then what we can do is, once we get the distance, we can get luminosities determined, like we did in these last examples. So here are the luminosities of stars, and then what we can do is we can compare it with surface temperature. When we do that, we find that for most stars, there is a correlation between surface temperature and luminosity. It does turn out that for 90–95% of the stars that we observe, when we plot surface temperature and in luminosity, we find that where they end up being plotted is correlated, and we call that the main sequence. So the main sequence refers to stars that show this correlation between their surface temperature and their luminosity. Now, this is because stars on the main sequence, we now understand, are stars that are in the earlier stages of their lifetime, and they're undergoing a fusion reaction of hydrogen to helium. So if I look at stars along the main sequence, the only thing that characterizes them is how much mass they've got. So these are stars that formed from less amount of hydrogen and helium. They have less mass, the fusion reactions are not as intense, and then as I move through the main sequence into stars with higher luminosity and higher surface temperatures, well, that's just happening because those stars formed from more material. So the more material, more mass, more gravity, more intense, greater luminosity, more intense fusion reactions, and as a result, greater luminosity. Now, there are stars that are exceptions to this. There are stars that have relatively low surface temperatures, but are still very luminous. And those we refer to as red giants. And the red giants are stars later in their lifetime that are undergoing different fusion reactions. So the hydrogen has kind of run out, at least within the core, and those stars are in the process of fusing helium into carbon and oxygen. So in these later stages in a star's life, the outer layers of the star are pushed outwards. So this is kind of that example we were looking at when we said, how is it possible that a red star and a blue star, these would be blue because of their surface temperatures, how is it that a red star over here could have the same luminosity as a blue star? Well, they both have the same luminosity because the fusion reactions are just as intense in both of those stars. This one is much more spread out. So it's so much, the outer layers have spread out so much that the result is that the outer layers are at a lower temperature. And so the light that's being generated in those outer layers is red. Now, one last thing I want to point out with these diagrams. These are referred to as Hertzsprung-Russell diagrams, HR diagrams. And when the diagrams were developed, the vertical axis is in luminosity, and notice that this is logarithmic. This is in terms of powers of 10 to be able to easily show the wide range of luminosity. So some stars are 1,000,000 times more luminous than other stars. They're generating energy 1,000,000 times more. And so as a result, we use powers of 10. We use a logarithmic scale to be able to represent that. Now on the horizontal axis, originally this was like spectral types in terms of wavelengths and peak wavelengths. What happened was that we now represent this horizontal axis in terms of surface temperature, but the surface temperature is backwards. Instead of increasing surface temperature to the right, increasing surface temperature is to the left. And that's kind of a bother, I think. I think it's time that we reverse the HR diagrams. I don't think that's happening anytime soon. Anyway, the correlation here, even though it looks like something that's got a reverse correlation, it's just because the temperatures have been reversed on the horizontal scale. Okay, is there a way we could use this diagram to determine the distance to a star? We go, yeah, once we recognize that, so for example, let's say we have a star at 7,000 Kelvin. So we've observed that the surface of the star has a temperature of 7,000 Kelvin. Well, if it's at 7,000 Kelvin, we know that only stars with a luminosity of 10 to the 27 watts are going to have surface temperatures of 7,000 Kelvin. So this is the only classification of stars that might have those properties. If I can observe that it has a surface temperature of 7,000, that tells me that it has a luminosity of 10 to the 27, and then I can observe how bright it is. If it's a fairly dim star, it must be far away. If it's a fairly bright star, then it must be reasonably close. So we can use that sort of information to find out distances. So we talked about distance measurement using parallax. Now we have distance measurements using, let's see what we got here. There is the peak wavelength. That's going to tell us surface temperature. And this is how bright the star is. Let's combine those together and use the HR diagram. Here we go. So we look at a star, easy enough to look at the spectrum of light. It peaks at 600 nanometers. Using Wien's law, we find out that the surface temperature is 4,830. Now if I go back and I look at the HR diagram, let's see, the temperature here was 4830. All right, 4830 puts us right in here. This is a little iffy, but what we're guessing is we have a luminosity, most likely, the luminosity is in this range. And so that's going to give us something like, I'm calling it 1 times 10 to the 26th. Okay. Okay, they're telling us that a detailed observation of the star suggests that it's on the main sequence. So it's not one of these helium-fusing red giants. It's still in the process of hydrogen fusion. And so I can bring this 4,800 temperature up to the main sequence, read over, and it says that the luminosity of this star is expected to be 1 times 10 to the 26 watts. Well, the luminosity can be calculated or related to the surface area of a sphere times the brightness. So I know what the brightness is. I know what the luminosity is. I can solve this for d squared. This tells me that this star is located 300 light years away. So again, because these things are all related, the luminosity, the actual energy output of the star, is related to, can be related to distance and brightness. So distance and brightness together is enough to figure out the luminosities. We can switch the equation around and solve for the distance. And that's how we can use the HR diagram to come up with distance. Now, we've talked about stars' lifetimes. This is referred to sometimes as stellar evolution. It's certainly not the same thing as biological evolution. What we're really saying is just the star goes through different stages. Those stages are often categorized in terms of what are the current fusion reactions that are ongoing inside the star. So when we look at a bunch of stars, we're making observations of stars that are in different points during their lifetime, during this stellar evolution. And by looking at all of these different stars that are going through different periods in their development, we can kind of piece together a picture of star formation when we have gravitational contraction of interstellar regions of gas and dust. Dust always confused me. That confused the heck out of me in astronomy classes of physics. Dust are just little tiny particles. We expect these are leftover. It's leftover debris from supernova explosions. So if you go back to the early universe, we said that all there was plasma when things cooled down, you had the formation of hydrogen and helium atoms, but not much else in the periodic table. It actually took generations of stars. Some of those would undergo supernova explosions and scatter heavier elements through the galaxies. So we'll talk more about that. But just for now, dust are small particles of elements other than hydrogen and helium. Now, when the core, gravitational collapse results in heating of the core, and when the core reaches about 10 million Kelvin, hydrogen fusion kicks in. So this is the formation of a star. As long as that fusion reaction continues, the star is going to be more or less stable against further gravitational collapse. Once the fusion shuts down, then gravitation can once again begin to collapse the material that the star is made from. So models suggest it takes about 30 million years for fusion to kick in. So for the formation of a star, from the time the gas collapses to the time when the core begins to fuse hydrogen, about 30 million years. Now, this really varies. So if we look at different regions of the main sequence, a star like the Sun, we expect could have fusion going on for 10 billion years. The low mass stars could be around for hundreds and hundreds of billions of years, maybe even a trillion-year lifetime. The really high mass stars, it turns out, run through their fuel very rapidly. They have a lot more fuel to work from, but they run through it very rapidly. And so they actually have shorter lifetimes. So I think we're coming up on time for a break, but let's look at one more slide here. So here is a star well into its development. And what has happened is hydrogen in the core has become depleted after, tens of millions or hundreds of millions of years of fusion. And so in the core now, helium is undergoing fusion. The hydrogen fusion is taking place in regions outside the immediate core, and then most of the star there's no fusion going on. So this is typically what we see going on inside the development of stars. Yeah, let's go ahead and take a break right there, and then we'll come back and we'll continue on looking at a star's development. If you guys have any questions, stop by.